Exercise 8. In this exercise, we're going to take a look at running SolidWorks simulation, the full-blown version, to actually see what torque or how torque reacts or works inside here. And so we're going to go ahead and bring up the part. So I'm going to open here, and better yet, I should have it up. We're going to go to the EA folder, just open up the EA part file. Okay, now with the EA part file here, go ahead and save this to the desktop. Okay, we're going to go ahead and run a simulation. This is actually like an applicator cap. And basically what we have here is we have this top that needs to be spun around and twisted off and popped off. And we're looking for the material to rupture around this area here, but yet it has a tether. And the tether is there to actually hold this part in place so it doesn't clog the nozzle. And this is very similar to an exercise we saw a couple weeks earlier that we were working on with Simulation Express. Now we're going to look at the right way to do it in the full-blown version here. So let's go to Office Products and start up SolidWorks Simulation. And click on the Simulation tab, and let's go to the Study Advisor here. Now also you'll see it's set to ABS PC. Let's go ahead and edit that material. We're going to go with an acrylic, high medium impact acrylic, and apply and close. Oh, also let's go back there. Also, just to take a look here, we'll set it to megapascals or MPa, and we can see the yield strength is at 45. And let's go ahead and hit apply and close. Also, what I'm going to do here, it's set to transparency. I don't really care for the transparency here, so I'm going to go ahead and take that off. Okay, so at this point, when we're looking at the training manual, it does go in and it talks about how to edit the materials and define custom materials and things like that. We're going to skip over that part. We're going to get right to the exercise here. Apply the fixed surfaces. And in this case, it actually is going to be, this is confined inside of another cylinder that actually has some stoppers that these are going to bounce up against. And then as it gets twisted, it tears this apart. We want to see rupture occur here. So let's begin with that. Underneath Study Advisor, hit the little arrow, go to New Study, and we'll just currently I'm only at static, which is actually fine because that's inside the torque. I'm going to go ahead and hit the green check mark here. And now what I can do is under Fixtures, I'm going to right click on Fixtures and I'm going to click on Fixed Geometry. Now the intent here is to get where the things are basically, these little faces are going to be contacting corners. Unfortunately, you can't see it if you did the previous exercise, which I believe is exercise 5. I might be wrong on that one. I'll have to double check. But basically, the applicator cap study that we did, and you'll get the grasp of what we're doing here. Okay, so then we have the fixed geometry. We hit the apply button, and we have our material. Now what we're going to do is under external loads, we're going to right click on that. And you can see we have pressure, torque, force, gravity, so on and so forth. We want torque. Go ahead and select torque. All right. Let's go ahead and follow the instructions here. As you can see here, what we're going to do is we're going to select for the faces to torque. We're going to select this face right here on the outside. And then here the axis or cylindrical face. Unfortunately, in the past, when I've tried to use the same axis, which you think you should be able to use, it doesn't like it, so you have to pick two of the same concentric cylinders or faces that you might have when it comes to torque. And it could just be operator error. But anyhow, also I'm going to go ahead and set it to English IPS, and the pounds, we're going to go ahead and set this up. Let's see what the book recommends. In this case, let me zoom up to this because it's been a while since I've done this. Okay, 20 pounds. So we're going to apply 20 pounds of torque. And you can actually see the little arrows there. Let's go ahead and hit the green check mark. And let's go ahead and run it. Now, if it's a very detailed part, do realize that under the mesh options, you have the ability to go to create mesh, and you might want to adjust the mesh depending upon the complexities of the surfaces that are there to get a better result. In this case, we're going to go ahead and just hit run and use the standard or default settings. Also be aware that a lot of these things could be removed and simplified. I didn't do that, like some of the fillets and things like that aren't necessary for this. But be aware that that would actually help, and you don't need all those fillets and radiuses and blends that are in there. Anyhow, let's get back to here. Now we can see the results here. Currently, turn that little guy off there. We see our yield, and I generally like to see it in megapascals or MPa, so I'm going to go ahead and double click on the rainbow. And first of all, I want to make sure that over here on the left, once you double click on that, you're going to see that we want to set to floating point. Some people like scientific notation, that's fine, or general. I'm going to keep it at floating. Then you could right click on the rainbow and go to edit definition. And then under von Mises stress, actually there's the meters, we want to set to megapascals or MPa. Hit the green check mark. Now you can see our yield strength was at 45. And here, anything that's in red is hitting about 46. And that's with 20 pounds. And we can see the red that is surrounding that area where we do want to see that actually rupture and pull apart from this, allowing the fluid, in this case this goes over a vial of fluid, and then that would allow it to exit the vial. Here we're though pretty close there. Probably going to take a little bit more because what we're seeing is we're getting to the point of plastic deformation, but it doesn't necessarily mean it's going to tear. That's really a little too close for comfort, so it's probably going to be a little bit higher than that. But as we can see over here, the actual tether, which we need to be intact because we don't want this just floating inside the applicator cap, is still intact. And so that's pretty much what the intention was here, to get that information. We'll go ahead and you can animate that. We can actually see that going through. Now I'm going to go ahead and hit stop. Some of the other things, do we want to see if we typically want to see if the red goes all the way through? Because if it doesn't, then obviously it's not working. So you have the ability to go in here and you could create sections. If you click on the section tool here, that does not necessarily do it inside this tool. So be aware that that section does not. Where you have to go for the sections is in the stress options here. Right click, and there's section clipping. If you click on this, you can actually see what's going on in here. In this case, the design is really not that great, because if you look at the point which actually the red is bleeding into here, it's actually going down. Maybe it's not the best design. This should maybe be opened up. Regardless, the intent here is to really kind of take a look at what's going on. The red is not bleeding all the way through. Thus, at 20 pounds, this is not functioning as we'd hope, because we want it to be less than that. So obviously the design needs to be changed, or the material can be changed as well. There's other tools in here as well. If you go to the stress and you go to ISO clipping, this allows you to see though that red area. And you can see there's only a very fine little red stripe where we're going into the plastic deformation area. The rest is really pretty much an elastic deformation, meaning it's just going to bounce right back into shape. In this case, we do want to promote failure in terms of it actually breaking. So there we can see that. It's kind of a neat little tool there. If you right click again, there's also the probe, which we really don't need to use in this case. We'll use that in a different application. But there we go. And so that is your exercise for today. Complete that. And then in the manual, make sure you go down and complete the case study. And so in this case, we have this toy. Roger's Toy Company, again, fictitious company, has hired us to analyze their latest design for a child's runabout toy vehicle. We quoted the job at about $3,500. Now I just threw that in there. That's not necessarily exactly what you would charge for that. Your task is to identify possible regions of failure, analyze the design, and if need be, enhance the design to prevent the steering wheel from breaking in the event of child applies more than 30 pounds of torque. Also, if possible, optimize the design to reduce materials and manufacturing costs. Write a minimum 2-page report. Actually, it should really be like a 4-page report because we want a cover page as well. Some of the things that you need to provide, because in this case, this is where you're trying to find that balance of performance and price. And really safety in this case, because it's just for a child's runabout toy. So you don't want it to break and injure a child. You want to make sure that it's strong enough to withstand the forces that might come in contact with, but you do want to try and reduce the amount of material. And here's the design you could see, and you'll find this in the folder that we have here in the case study. I'll go ahead and I'll open it up and I'll just get you started on it. And as you can see here, it might actually be a little too thick, and it does not coincide with the proper designs when it comes to plastic, of course. That these the 60% rule, where these need to be 60% thickness of the actual walls. So there's some issues here. Essentially, let's go ahead and set it up very quickly for this and test it out. So I'm going to go back to new study, static, hit the green check mark, and from here we'll go ahead and the material type is listed in the book. In this case, acrylic we're going to go with. So let's go ahead and under the toy steering wheel here, right click, apply edit material, and you want to go with plastics, where you'll find the acrylic, medium high impact. So at MBA, just take a look at what you're looking at. You're looking at 45. Hit close. Again, if you want to get rid of the transparency, just right click and click on this little X here on the body. That will bring back the original colors. And from here, now we could go ahead and set up our problem. So for the fixtures, let's right click on the fixtures and go to fix geometry. Now the steering wheel is going to be locked into a post that's coming out of the actual runabout vehicle. And we could pretty much figure it's probably this is going to be fixed. Okay, we can even do the top if we want. It's going to be locked in there. And we could go ahead and hit the green check mark to apply. The next thing we're going to do is we're going to go ahead and take a look at the external loads, right click, and again we want to go with torque in this example. And for the faces to torque, let's go ahead and select this face, and then of course the axis will be this face on the outside here. You can see the arrows spinning around. Unfortunately, like I said before, sometimes it doesn't let you use both in my experience, but you could try it if you like. Go to English IPS and the pounds. Again, we'd have to figure out what this is, but the customer already gave us a spec, about 30 pounds of torque. So let's go ahead and put in 30 pounds and hit the green check mark to apply. Run it. And again, you probably want to remove a lot of these fillets and things like that. Those things aren't necessary. Running these analyses, they actually take up more time. You could really simplify it quite a bit by defeaturing it. Okay, and here we have our mices. Again, I'm going to right click up here. By the way, if you want to set this up to where you don't have to always right click on this area to change the megapascals, you go to simulation and you find the options. And in here, if you go to the default options and plot, this is where you start to see the ability to change some of those things. So for example, here we want floating for the number format, and then the static plot, we'll set this to let's see here. Actually, let's see, it would be the it's fleeting me today. Okay, we could set it to English IPS here. And here we go, under pressure stress, just set it to MPA. Hit OK. I know that's a mix and match there, but like I said, the material data sheets are very useful. You could look up the MPA instantly pretty quickly on most things and find it. All right, but so we still have to change this because we right click, go to edit definitions. So right click on the rainbow, over here on the left, set it to MPA, the green check mark, and then If you right click here, I think it already is set, so we're pretty good. Actually, if you double click on the rainbow on the left, just make sure it's set to floating. And the decimal places, you can increase that to 2 or 3, depending upon your precision that you're interested in. Okay, in this case, actually, you know what? It's kind of thrown. I don't necessarily want to see that much. Go back to 1. Okay, so the yield strength is at 45. Now remember, that's when you start seeing elastic deformation take place. It's going from elastic to plastic deformation, meaning it's not going to bend back once it bends past a certain point. But it's not complete failure necessarily. We're looking at 45, and so 45 is way up here, and we're only down to 7. So this is over-engineered. Now again, for a child's toy, if there's a potential for a child to get injured, you do want to over-engineer it to some extent. But be aware that sometimes, 4 times or 5 times that amount is not always necessary. So we might want to actually try and reduce some of the material costs here. So let's do that. Now to do that, here, just go back to the model by clicking on the model tab. And let's just do a quick little fix here. Maybe we could reduce the actual wall thickness. Just double click on this surface here, and we can see the actual wall thickness. It's set to 0.1. Let's say we want to set it, let's try 0.06. The rebuild button. See, it will get thinner. Okay. Oh, also, actually, let's undo that. Here's another thing. This is how you could prove out to whoever you're working with that, hey, I could reduce the material costs here. Remember, you could always go to evaluate. Go to the mass properties when you start off with the initial design. And as long as, in fact, make sure that under the material here that you specify, by default it goes with like a material that's similar to ABS plastic, which is fine, but you want to get more accurate than that for the actual weight of the toy. So in this case, we said it was going to be acrylic, apply, close, and now if we go ahead and go to mass properties, we could see the mass here. We have 0.2 pounds, right, of material. Let's see if we could reduce that. So if we go back and we're going to redo, I can't redo it, so I'm going to just go ahead and double click on the surface, find that 0.1. We'll change it to 0.06 again and rebuild. So we thin that out. Let's get rid of that transparency there. Okay, also some of these aren't really necessary in every single position. So we could go in here, and since it's a SolidWorks native file, just right click on circuit pattern, edit the feature, and if we go to instance vary, not instance vary, I'm sorry, instance skip. We could take out some of these that aren't necessarily like this. Oh, unfortunately, it was designed in such a way that we can't remove that one just now, but we could go back and edit the way it was modeled. But let's just say we'll take out these ones in the middle that we really don't feel we need. That one we could take out later by just adjusting it, the angle at which it was positioned. Go ahead and hit the green check mark. Now, some of these things could be reduced and adjusted as well. So, for example, the ribs. There's a 60% rule, so technically we want to remove, if it's 60 thousandths, we'd have to adjust that, or in this case, the whole thing was 100,000. Let's go ahead and make this 0.0. I think it's going to blow up. It's going to probably lose a lot of the fillets when I do this, but let's go with 0.05 for the wall thickness. Hit rebuild. And of course, we do get a few error messages, which we'll deal with. They're just fillets. Unfortunately, let's edit that feature. And we'll just get rid of the fillets. And we do not need the fillets for the analysis. Be aware of that. Those are just excess. Also, if you're leaving fillets in with errors, remember you could slow down your system by 10 times. So either suppress them or delete them. Just get rid of them if... Okay, so we've reduced some of these things. Also, this could be adjusted. I mean, that doesn't need to be that thick. But let's just go ahead and, first of all, let's look at the mass properties. The mass properties, we got it down to almost 80% of the material we've removed. So think about that material cost. If you're going to make tens of thousands of these things, you just saved the company a lot of money. But is it better part? Is it still going to fail? Is someone going to get hurt? Let's go back to the study here. Okay, let's rerun. Okay, and if we look at the yield strength, still at 45. Before we were at about 7.5, I believe, when it came to the yield that we were experiencing, and here we're at 11.3. This is still pretty well engineered. It's a very strong part. We've saved a significant amount of material costs, but yet it's still within our safety region. So again, a lot of this is up for discussion. Work with the engineers. Don't just make the assumptions, because garbage in is garbage out, is what I say, and what everyone says when it comes to this. If you're not doing these things correctly, it could be catastrophic results, and just be very careful when you're designing these things. And that is your lab or your case study to work on. Continue to get that down and improve upon that design. Maybe reduce some of the material costs. Write a paper on it and give me the feedback. Also show me those under the evaluations, the mass properties before and after, to see how much you were able to reduce the material costs by, and make sure that we see the unlicensed MPA here. And that concludes this exercise.